you all, and hi guys, and welcome to our second seminar on image processing and applications. I'm Matilde Anthony, one of the MATLAB student ambassador at the University of Genoa. I'm an aeroengineer student, and today we will see three different topics: edge detection, circuit detection, and geometric transformation. So in the first section we will see the definition of what is an edge and the detection of objects in an image. So first of all, we have to define what is an edge. So an edge is an area with strong intensity contrast. So for example, if we take into considerations this image, we can see that if we take into consideration two near pixels, for example these two, the two pixels will be characterized by different intensity values. The first one is characterized by a value that is equal to 202, and the second value is equal to 60. So I think that you can see that you can notice that there is a high difference in intensity between these two pixels. So there is a strong intensity contrast in the image. So why edges are the edges so important, and how can we find an edge? So a method to find an edge is the subtle one, and in this case we want to, as we can see here in the figure, we want to compute the intensity gradient in the y direction and the intensity gradient in the x direction. So we will find the jy and jx that correspond to the gradient in the y direction and the x direction. If we want to compute the intensity gradient of all the image, we want to compute it with the square root of the sum of the jx squared and the jy squared. If we want finally to compute the edges, we have to compare the intensity gradient with the threshold. If the intensity gradient is superior to the threshold in magnitude, we will have an edge. So if we want to implement this in MATLAB, and if we want to know better what is an edge and how I can find an edge in an image, we can start from an example. So we can load an image in our workspace. To load an image in our workspace, we can use Hemisphere Function that allows us to load the function, load the image reading from a graphics file. So in this case, the Hemisphere function requires as input the file name that we want to consider. In this case, circles point png. After loading our image, our grayscale image, that is circ, we want to visualize it and we want to display it on the monitor. So how can we do that? We can use the Hemisphere function that requires as input the image circ, as we can see here in this line. To be precise, we can also add a title to identify the images we are considering. So in this case, we are considering an image that represents the three circles with different intensity, and so it is useful to set this title with the function title that requires as input the string of the title. So now we have displayed the image that we want to analyze. We have three different circles with different intensity. I can find the edges of these three circles with different intensities with the function edge, as we can see here in these lines of code. With the function edge, we know that we can find the edges of the three different circles. The function edge requires as input, obviously, the image that we want to consider, so circ. And if we don't specify the method that we want to use, we can use the default one, that is the Sobel method that we saw before. So if we want to find an edge, we will find it thanks to the gradient, the intensity gradient in the image. So first of all, we can apply this function. We apply this function to our image, and we will find a circ edge that is a logical array which presents 0, that is composed by 0 and 1 values. The 0 value corresponds to the point in the image that don't present an edge, while the 1 values correspond to the point of the image that has an edge. In this case, if you want to represent, if you want to visualize only the edges of the image, we can do this with the Hemisphere function that requires as the first input the circ edge that corresponds to the logical array that represents the edges. So we have found with the Sobel method, and with the Sobel method, that is the default method, the edges of the circles. But we can see that only 2 circles are displayed here, and the first one that corresponds to the circles with the lower intensity, with the lowest intensity, is not represented. So the edges with lower intensities are not recognized. How can we recognize them? We can recognize them if we lower the threshold. First of all, we have to know which is the default threshold used for this case, because we haven't specified that. To know the default threshold, we have to repeat the same comment as before. So the edge function with the input, which corresponds to our image, our grayscale image. And we will have 2 different outputs. The first output corresponds to the same output as before, so the logical array that corresponds to the image that represents only the edge. And the second input, the second output will be the default threshold that has been used to detect the edges in this method. Now we see we have the default threshold, and we can lower it in order to detect only also the edges for the first circles. So first step, the first line of code. So we have to lower the threshold. We can consider the default threshold, that is thresh depth, and we can divide it, for example, by 3. In this case, we will obtain a new thresh new, that is the new threshold that is lower than the default one. in this way, we will repeat the same command as before. So we will repeat the function hedge with the first input, that is circ, that is our image that we want to analyze, and we will specify also the threshold, the lower threshold that we want to consider this time. So trace new. If we want to visualize this new result, we can use another time show, but in this case we will visualize the new hedges. So as we can see here in this result, we will obtain the second and the third circles, the hedges of the second and third circles, but also the edges of the first circles that was the circle with the hedges with the lowest intensity. So we can see that if we lower the threshold, we can detect also the hedges of the first circles. Now we can use another method. We saw the Sobel method. Now we use the Laplacian of Gaussian method. So another filtering. Now we see that we use the function edge, and that requires as a first input our image, that is always the same image. And as second input, this time we can specify the method that we want to use. So we knew that the default method was the Sobel one, and now we want to use another method, that it is the Laplacian of Gaussian. So log. If we specify this method, we will obtain two different output. So the hedge nu2 that represents the hedges that we can find with this log method, and the threshold that that has been used. After we can, as always, we can visualize the result thanks to the Hemisphere function. And we can put the hedge nu2 as to be visualized, and we will obtain this result. We see that we obtain the same result as before, because we have 3 circles as before, but there is an advantage in this method, because if we consider only the first circles, we see that in the Sobel one with the lower threshold we have hedges that are broken up. But if we want to if we want not to have broken up hedges, we can use this log method. The problem is that if you can see, if you see here in the image for the second and the third circles, we can understand that there is a little bit of noise. So to reduce noise with this log method, we can raise the threshold. So we consider another case. We repeat the command. The command is always hedge. We consider always the same image, that is circ. We specify the method, that is in this case is log, and the third input corresponds to the threshold. So in order to consider less noise, we will raise the threshold. So in this case, we can, for example, put the threshold multiplied by 2. If we want to consider the situation, the previous situation, and compare it with the higher threshold, situation, we can use the Hemisphere function, as we can see here, and we can, in this case, we can see the previous image next to the new image, thanks to the command montage inside the function Hemisphere. In this case, we can have two different images, one next to the other. So we can see here that in the second image that corresponds to the new image, we have less noise. And so this is an advantage. So we have said the definition of the edge detection, and we have seen why edge detection can be useful. But now we can see also the circle detection, and we will see circle detection to detect circular objects in our image, but also to use the circle detection to solve mathematical problems once we have the size of the objects that are present in the image. First of all, we can start from an example. So we load an image, and we load an image and we display it the image. The image will represent, as we can see here in the figure, lots of coins. So as before, we use the Hemisphere function in order to read an image from a graphics file, and after we will display it with the Hemshow function. We see that the result will be this grayscale image. Our aim is to detect the coins that are characterizing this image, and we will see how it is possible to do this. And we see that first of all we have to set a radius range of the radius of the coin, and we will have a range to consider. So we will have the radius range from the 12 from 12 pixels to 40 pixels. This range will be useful because of we will use the infinite circles functions. So we have to see how infinite circles functions can be used. This function is useful because we will have as output cent and rad. This cent and rad are two different arrays that correspond to the centers of the center coordinates of the coins in the image and the radius value of the coins in the image. How can we get them? We can get them thanks to the infinite circles that requires as input, as first input, obviously the image that we want to consider, and as second input the limits of the radius of the limits of the radius range that we are considering. So in this case, we are considering the radius range of the coins from 12 pixels to 40 pixels. In this case, we can see that if we implement this command, we have the result of cent and the red that are two empty arrays. Why is the result like this? We can see that these two arrays are empty because by default we know that the infinite circles function detects circles which are brighter than the background. Here we see that the coins aren't brighter there, than the background, but they are darker than the background. To find these circles in the image, we will have to set this we will have to specify the object polarity. So the object polarity will have to be set to dark. Because we have to remember that the circles, in our case, the coins, are darker than the background. So we will repeat the line of code in 5 circles that requires as first input the image coin, as second input the limits of the radius range, and as third input we have to set the object polarity, in this case dark. And we can see that sand dark and red dark aren't empty anymore. And so we have obtained the centers and coordinates of each coins, and the radius values of each coin. Now that we have found the centers and the radius of each coin, we want to visualize this coin and this circle detection. And we can achieve this result thanks to the image, thanks to the these circles function. So first of all, we have to visualize our image. So we will use another time show coin that will represent our coin image. After, we will add the line of code these circles, and that requires as first input the center that we have found, and as second input the radius that we have found, and as the third input we can specify the color of the circle that we want to that we want to draw around the coin. So in this case, green. And so in this case, we will achieve this result. We will have our image with lots of coins, and we will have the circles around the coins that have been detected, circles that are green, thanks to the this circles function. Okay, so now we can go on. And we can go on because, as we can see here in the figure, we have detected all the darker objects, but the brighter objects haven't been detected. How can we detect also the brighter object? We can reach we can achieve this result thanks to an increase in sensitivity. So we repeat our command with the infinite circles, but we will add we will specify sensitivity, and we will set the sensitivity to 0.9. In this case, we see that the sensitivity parameter has a value between 0 and 1, and the default sensitivity parameter is equal to 0.85. So if we want to increase the sensitivity, and if we want to visualize and detect also the brighter object in the image, we have to increase the value from 0.85 to 0.9. How can now we can see the difference thanks to the subplot. The subplot allows us to divide the current figure in this case in a 1 by 2 grid. And in the first position of the subplot, we will see the image with the default sensitivity, while in the second position of the subplot, we will see the image with the 0.9 sensitivity. And in fact, we can see here the difference between the first image and the second image. If we can see this coin that is brighter in the first image hasn't been detected, while in the second image the brighter coin has been detected. Now we can go on, and we can imagine to distinguish the smaller coin and the smaller coin and bigger coins. So imagine that, for example, the smaller coin corresponds to 1 euro, and bigger coin corresponds to 2 euros. So if we wanted to distinguish in the image the smaller coins with the color blue and the bigger coin with the color red, we can do this with a few lines of code. So we can start from the first line. Here we have to set a threshold. In this case, we want to create our threshold taking into account the limit that we have set before. So lim1 that corresponds to the first limit, the minimum limit of the radius range, as you remember, that was the 12 here. Now we can multiply this value, and it will be multiplied by a quantity equal to 2.3. We will obtain our threshold, and we want to compare this threshold that we have created now with the value of radius that have been found before. So red sense, as you remember, is the array of that contain all the radius value. These radius value are compared with the threshold value that we have set, and if this radius value is less than the threshold, we will obtain all the indices of the smaller coins. Why this? Because we can see that we are creating in this way a logical array that is a IDX small. This logical array IDX small will have 0 and 1. 0 corresponding to the position of the bigger coins, and 1 corresponding to the position of the small coins. So if we proceed in this way, we see that if we use the not operator in front of the IDX small, we will obtain the opposite situation. So we will have a logical array with 1 and contain 1 and 0 values, but in this case the 0 will be in the position corresponding to the bigger coins, while the 1 correspond to the position of the small coins. Finally, we have found two different logical arrays that represent the indices of the small coins and the indices of the bigger coins, respectively. So, if we want to visualize as before the coins and the detection of the coins, we can visualize the coins with the himshow command and the detection of the coins with the v-circles command, but in this case we will use the two different colors to distinguish small coins that correspond to 1 euro and the bigger coins that correspond to 2 euros. So we will use twice the v-circles command. And in the first time, we will extract only the center and the radius corresponding to the indices of the small coins. And we will use the color blue for the small coins, while we will consider the second command v-circles, and we will consider only the bigger coins indices and for the centers and for the radius. And another time we will change the color because we are considering another type of coins, in this case the bigger one, and we will have the color red. So in order to be precise, we can add to the image the text 1 euro and 2 euros here in the image. So to add this text, we can use the function text. We have to define the position of the text in the figure, in the figure. So 10 pixel and 20 pixel for the first text, and the position of the second text will be 50 and 20 pixel. After as third input, we will consider the text that we want to display, so 1 euro and 2 euros, and after as the fourth input, we can use the color, we can specify the color blue for 1 euro and red for 2 euros. We can go on, and we saw that if we want, once we have found the distinction between 1 euros and 2 euros, we can solve simple mathematical problems. So, for example, if you wanted to compute the if we want to compute the amount of euros that is represented in this image, we can do in these few lines. We can, in fact, we can use the non-zero function that requires as input the ID x small. And the ID x small is a vector, is a logical vector composed by 0 and 1. 1 represents the position of the smaller coins. So if we use the non-zero function, we will count all the non-zero values inside this vector. So we'll count the number of small coins. We can proceed in the same way for the biggest coin, the bigger coin corresponding to 2 euros. But in this case, we will multiply. The discount will be multiplied by 2 because we are considering coins that have a value equal to 2 and not equal to 1 euros. So if we wanted to obtain the total number of euros inside this image, we can sum n1 with n2, and we will obtain n tot that corresponds to the total amount of euros inside the image. in this case 54 euros. So now we can go on and we can arrive to the geometric transformation, that is the last section of this seminar. We will see today has the geometric transformation, rotation, translation, and scaling. When we consider geometric transformation, we have to consider two different images, the moving one and the fixed one, as we can see here in the picture. So why are geometric transformations so important in image processing? Because when we take photos of the same object, we can take them in different ways. We can be near the object or far away from the object, and we can also take photos of the same object with different devices. So we will obtain photos of the same object, but the photo will appear different from one from the other. So we can use a geometric transformation to compare these photos of the same object. So now we can implement this concept in MATLAB, and we can start from an example. So first of all, we have to load another time, in this case, a biomedical image of an eye scan before and after modification, and we'll display one next to the other. So we have to so first of all, we have to use another time emerge function to load the image in the workspace. We will have in this case two different images, the high BEF and the high EFT. The high BEF is the original image, while the high EFT corresponds to the same image but after some modifications. To understand which modification have been applied to the image, we can use the him-show pair that allows us to see the picture one next to the other thanks to the montage command. So in this case, we can see firstly, we can see that the second image, that is the image with modification, that is rotated, that has been rotated of 90 degrees clockwise. So in order to take this image back to the initial position, we have to apply the opposite geometric transformation. So first of all, we have to use the function imrotate. The function imrotate will have as the first input high EFT that correspond to the image with modifications. So the second image, this one, and we want to rotate it 90 degrees counterclockwise. So we wanted to do the opposite operation that has been done before. In this case, we know that positive angles correspond to counterclockwise angle of rotations, and the angles are measured in degrees. So if you want to see this rotation, we can use another time him-show pair with the original image, so the first image here, and the second image now will correspond to the image with modifications, but rotated of 90 degrees counterclockwise. And we can see actually that we have the same image in the same position as the original one. But we can understand that there are other modifications to do to the second image to take it back to the original one. For example, we can see that this image is zoomed out, so we have to scale this image. How can we do that? We can use the function imresize. The function imresize requires as first input the image that we want to consider. In this case, I have 19 that corresponds to this image, the second image. After, we have to specify the scaling factor. The scaling factor will have a value that is greater than 1 if we want to increase the size of the image, or less than 1 if we want to decrease the size of the image. Here, we understand that we want to increase the size of the image. So we will have to write a scaling factor that is greater than 1. So we have chosen 1.15. If we want to analyze and if we want to visualize the result, we have to use the Hemisphere function that allows us to see the original image next to the modified image after a rotation and after a scaling, and we see that this image is more and more similar to the original one. Now we can see with this first picture that actually we have now we have two similar images, but we can do also a translation if we wanted to have a perfect if we wanted to have two images that are perfectly overlaid. So first of all, how can I realize this image before translations? We can take into account two different images, so this one and this one, so the height come before and after modifications, and I want to overlay the second one above the other one. If I want to do this operation, I can use the imshow pair without the command montage, and this command will allow me to represent an image and overlay the image above the first image. So a pink, if you can see a pink image and a green image, and we can see that now they aren't perfectly overlaid, but we can do a translation, apply a translation in order to have the pink image and the green image perfectly overlaid. To achieve this result, we can use the imtranslate function. Imtranslate function requires as input the hi-hat 90 res, that is this image that we are considering. So the image that is more and more similar to the previous one, to the original one. But now we have to we want to apply a translation in the x direction of 5 pixels and a translation in the y direction of 5 pixels. So we can consider a positive translation in if we move in right way or in down way, or we are moving down. So in this case, with this translation, we will obtain to perfectly overlaid image. How can I see it? I can see it thanks to the Hemisphere pair that we have used before, and we will have as first input the original image, and as second input the image that has been used for the 3 different operations that we have done. So the translation, the rotation, and the scaling. And after these 3 operations, we can see that the two images, the pink one and the green one, are perfectly overlaid one above the other. So I don't know if there are any questions. Maybe I can see it. Okay, I think that there is no questions. So I hope that the seminar that you like the seminar, and remember to follow us on our social media, so on our social network account, so on our Instagram page and our Facebook page. You can see the link on the description of the video. So if you have any questions, you can email us, and you can reach us thanks to the social network media on Facebook and on Instagram. So I hope you like our seminar, and if you have any question, you can contact us. I think that we can finish here, and I hope to see you again for the next seminar. Stay in the loop, contacting us on the Facebook and on Instagram. So bye bye.